Thank you very much for coming. I'm gonna talk about Hermitian sum of squares on finite sets. This research is joined Mauricio Velasco and David Corredor. It was my master's final project. Okay. So I will speak about what are Hermitian sum of squares, coloring problems, an upper bound theorem for H SOS multipliers, and scalability and approximate dynamic programming. So for beginning, I will speak about coordinate rings of finite sets. Fix a positive integer n and a finite set x in C to the n. Let the coordinate ring of x be the set of all polynomials with complex coefficients restricted to the points of x. It means the coordinate ring, the ring of polynomials in n variables modulo its ideal. Since x is finite, every function f from x to c can be represented by polynomial. So we can think the coordinate ring of x as the set of all functions from x to c. Conjugation, we will assume that this set x is closed under conjugation component-wise. It means that for all x in x, x bar or the conjugate of x is also in x. Equivalently, this means that the ideal of x is generated by polynomial equations with real coefficients. And if f is a function, any function from x to c, we can define the conjugate of x or f bar by conjugating the values of f. And this operation defines an involution from the Cartesian product of c of x and c of x, from c of x to c of x, and this involution is a ring isomorphism which applied twice is the identity. So I will say some main characters of this talk. Let f a function, a polynomial of the coordinate ring of x, and let A as vector space of the coordinate ring of x. We say that f is real valued if the conjugate of f is equal to f. We say that f is non-negative if it is real valued, and for all x in x, f of x is greater or equal to 0. And we say that f is Hermitian sum of the squares of A if there exists an integer m and elements q1 of qm such that f can be written as q1 times the conjugate of q1 plus blah 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 qn times the conjugate of qm, and that is equal to the sum of the norms of qi squared. Our main characters are the following convex cones: the cone P of non-negative elements of C of x, and the cones sigma A consisting of the cones of Hermitian sum of the squares of A, where A is a subvector space of the coordinate ring of x. So why is important to speak about P? So P allows us to model all optimization problems on X. A general optimization problem, you know, on X is of the form, given a real valued function g in C of x, we find alpha equal to the minimum over all x in x of g of x. And we can reformulate this problem, the optimization on the cone P, by reformulating it as alpha is equal to the maximum of lambdas, where g of x minus lambda is in P. So if we had a good description of P, or at least a good membership algorithm in P, we could solve the polynomial optimization problems on X. But you know, this is difficult. The sigma A are important because they are all contained in the cone P, and it admits a good and approximate good membership algorithm via Hermitian semi-definite programming. So, in words, each cone, sigma A, gives us easy proofs of the fact that some polynomials are in P. This is the idea. Since X is finite, note this, every non-negative polynomial is a sum of Hermitian squares. This is a fact related to these polynomials. The Kronecker delta are polynomials in this coordinate ring. So you can write every function f of x in terms of these Kronecker delta polynomials or functions. Such certificates are very large. Oh, yes. So we wish to choose smaller subspaces A to certificate that one polynomial is non-negative. I will speak about multipliers. An element F admits a Hermitian sum of squares multiplier from the subspace A if there exists non-zero G in sigma A and H a Hermitian sum of squares such that F times G is equal to H holes. We say that F admits a strictly positive Hermitian sum of squares multiplier from the subspace A if there is a strictly positive G and H such that this equality F times G equal to H also. If F has a strictly positive Hermitian sum of squares multiplier, obviously F is not negative. And this is our main result. No, this is not our main result, but for the main result of this talk, that guarantees the existence of multipliers supported on a given subspace, we need some definitions. The product and conjugation are from elements of the subspaces. So we say if A and B are subspaces of the coordinate ring of X, we define A times B okay, and this is our main result with Mauricio. Let A and B subspaces on C of X. If F is in A times the conjugate of A and F is a real valued function and is strictly positive on X, and this inequality holds, we say that F admits a Hermitian sum of squares multiplier supported on the subspace B. So why is important this theorem? Because this theorem transforms a semi-algebraic problem, the existence of multiplier, into an algebraic problem, which is much simpler. This problem of calculate this dimension of these vector spaces. This is our main example. We take as X this set named the these roots of unity and hypercube. This set is the variety with this equation xi to the d minus 1 equals 0. And obviously the coordinate ring of U, when I refer to this set, is the ring of all polynomials in n variables modulo the equations of the roots of unity in each variable. The conjugation, when you take xi conjugate, it is equal to xi to d minus 1. Yes. Why is important to study this set? Okay, this is a motivation. Suppose you are an academic coordinator of a university and you are in a charge of assigning final exams of the following subjects. You have vector calculus in the first point, linear algebra, Pascal, Blaise Pascal, classical mechanics, Borges and Homa. And the university give you give you 5 time slots to organize the final exams. 8 to 9 p.m., 9 to 10 in red, 10 to 11 in green, 11 to 12 in violet, and 12 to 1 a.m. in black. And so you can address this problem doing a graph G, where the nodes are the subjects. We will say that 2 subjects are connected if they have at least one common student. According to the university information, this is a fiction, our graph is so. Yes, this is our graph. You can see vector calculus is connected with classical mechanics. So there is at least one student seeing vector calculus and classical mechanics, and in the same way between Borges and Homer. So color to assign optimally the courses of the time slots. So this so this graph is tricolorable if there is sorry, where is it? Yes. Here. Sorry. This graph is tricolorable if there exists X in U63. Like 1, 2, 3, 5, 6, 7, 6 will be the variables. So you can see, you can modulate this problem like this. Okay. So it is easy to assign to each subject a vertex and to each color a 3 root of unity. It means associate an element of U3n to a 3 coloration of the graph. And the graph is tricolorable if and only if alpha star is equal to the E, where E is the edges and N is the vertices, and this equation alpha star is equal to the maximum over all X in U3n, and yes, this is. Okay, more generally, you see, alpha star is integer valued and counts the maximum number of edges that can be colored correctly using 3 colors. The previous lemma, this lemma shows that bounding the optimum of this quadratic Hermitian program is NP hat. That's quadratic in some way. So I will clarify this. So to clarify this, we agreed to write C over dz as follows, as C over dc is equal to 0, 1, minus 1, of the integer part of d over 2 and minus integer part of d over 2, instead 0, 1, 2, 3 of d minus 1. And we define the following bijection between C over dz to the n and the monomials of the coordinate ring of U. And for each vector, I will send to the monomial, to the exponent of this vector, where the monomial of the CU denote the monomial basis in C of U. We have 2 notions of degree associated with 2 different norms. I will explain the 2. The first one is the diamond degree. For a monomial x to the a in CU, we say that the diamond degree of this monomial is equal to the sum over all absolute values of its terms. According to this, we say that the diamond degree of f, any polynomial as the greatest degree between its non-zero monomials. So as an example, the diamond degree of this polynomial is equal to 11 because the second monomial is 5, 4, and 2. 5 plus 4 plus 2 is equal to 11. The second notion is associated with infinity norm, and we will call this one the cubical degree. So the cubical degree, you take a monomial, and the cubical degree of this monomial is the maximum of the absolute value of its components. And according to this, we define for any polynomial of the greatest degree between its non-zero monomials. You take the same example, and here the diamond degree of this polynomial is 5, because the second term, the maximum component is 5. So we define the sets A, K is equal to the set of all polynomials in C of U, such that the diamond degree of f is less than or equal to k, and similarly b of k equal to all polynomials of C of U, such that the cubical degree of f is less than or equal to k. Note that AK and BK are invariant under conjugation math. You can check this. And moreover, AK and BK are sub-vector spaces of C of U. And there are n times the integer part of d over 2 plus 1 degrees with the diamond notion. And there are the integer part of d over 2 plus 1 degrees with the cubical notion. Always there are more degrees with the diamond notion. So our first theorem, rewritten with this notion, can be seen like this. Let f a real valued function. It means that f is equal to the conjugate of f, and a strictly positive function on U. Then there exists a Hermitian sum of the squares polynomial G in sigma A, such that f times G is Hermitian sum of squares. And if you consider this polynomial and denote n, it's the sailing part of the positive root. This polynomial has two roots when n is even and just one root when n is odd. You can check this, and you take the positive real root of this polynomial, and you take the sailing part of this positive root, and you can reformulate the theorem as this: let f a real valued and a strictly positive function in U. Then there exists a Hermitian sum of squares polynomial G in the version of the cubical degree in sigma Bn, such that f times G is a Hermitian sum of squares. So the question is, what is better to use, the cubical degree or the diamond degree notion? To understand the meaning of better here, we must remember that f times G equal to h when G and h are Hermitian sum of squares can be translated to f times x star ux equal to x star bx, where u and b are Hermitian semi-definite matrices. According to our theorem, the dimension of matrix U is, when you use diamond degree, the dimension of this A squared, and when you use cubical degree, Bn squared. So which is smaller is the question. And according okay, in conclusion, when these 2 or 3, it is better to use diamond degree, since all polynomials have cubical degree 1. For simplifying this, note this monomial x1 times x2 times x3 times xn is equal to 1 because the maximum component is 1. So it's ridiculous to use the cubical notion here in these cases when d is equal to 2 or d is equal to 3. However, when D is between 10 and 4, and N is between D plus 1 and D, our experimental computation shows that always it is better to use the diamond degree notion. So when D decrease, I think it is not proved in this moment, it's better to use the cubical notion, sorry. The cubical notion was a typo. Okay, so I will give an idea of this theorem. Let me remember the theorem, the central theorem of this talk. And so let A and B be subspaces of the coordinate ring of X when X is a finite set. If F is in A times the conjugate of F, A, and S is a real valued polynomial and strictly positive on X, and this inequality holds, so then F admits a Hermitian sum of the squares multiplier supported on the subspace B. I will do a contraposition argument. So suppose that F.
So in principle, you have many choices. You don't have to limit yourself by degree to the choice of the subspace of multiplier, right?
Yes.
Is there any way that you know how to optimize this choice given the function?
Yes, given a function, you can optimize the choosing of these subspaces. Yes, you are right. But that depends the function, and this is interesting.
Right, well, maybe given a subspace, how do you choose? Like let's say you're given a subspace, like in your theorem, you have your subspace, and then you want to know for which, how do you find like the smallest subspace from which all of the multipliers will get?
Yes, you are right. This is a better yes, this is, yes, you are right. How to say it? Yes, it's true. We are trying to do this with some polynomials specifically to take the small subvector space and to research upper bounds. Yes, and this is another approach that is the sum of the squares multiplier supported on the subspace B. So that means that F times sigma B intersection sigma AB is equal to 0, is equal to a singleton 0. And you can see a linear functional between these two cones. By Banach's separation theorem, there is a linear functional such that L in this cone is greater than 0, strictly greater than 0, and in the other cone is less than 0 or non-zero elements. You can prove that there is a subset Z in X such that your linear functional can be written as the sum of all over Z and Z, or with some weights and point evaluations. And the number of elements of C is equal to the dimension of A times B and the conjugate of A times B. We denote n plus the number of strictly positive coefficients AZ of these weights, and then n minus the strictly negative coefficients. And we define this Hermitian form BL. BL of HG is equal to L of H conjugate times G. You can see that the number of the signature of this Hermitian form is this is just a remark, is the largest dimension of the vector subspace W, the subset of B, where BL is positively definite, and it's the same for the negative definite. And considering the basis F of Kroneker's delta of PIs in C, we can observe that the signature of this matrix is precisely the coefficients of above. Yes. So since BL is negative definite on AB, that means that G in AB, then BL of G in AB is equal to then L of conjugate of J times G is less than 0, then the dimension of A times B must be less than or equal to the signature, negative signature of BL. In similar way, we define BL of F. It's very similar, this bilinear form, and it can be proved that the eigenvalues of BLF are of the form these weights times F of Z, the value of F for each Z in Z. And therefore you have that the positive signature of BL is less than or equal to the positive signature of BL. And applying the same argument as above, you obtain that the dimension of B is less than or equal to the positive signature of BL. And then you obtain the following inequalities. And if you sum in both sides of the inequalities, you conclude with the theorem. So this is the idea of the theorem. In the next part of the talk, I will speak about an approach, an approximate dynamic programming approach. This is because with the current Hermitian SDP solvers, Hermitian SOS multipliers are capable of establishing the chromatic numbers only in small graphs. Yep. Which allow us to use our positivity certificates as graph coloring heuristics in a method for finding good colorings. And we call this resulting algorithm rollout algorithm with lower bounds. So to explain the dynamic programming model, suppose you want to color the following graph of 4 vertices. For our dynamic programming model, we give an order or enumeration to the graph nodes. And this is the dynamic programming model. A dynamic programming model associated with this graph can be described as this, with some states. These states are partial color graphs. They symbolize that you has colored the graph 1, the node 1. And here you have colored the nodes 1 and 2, but with different colors. The parenthesis symbolizes different colors.
Maybe you can draw the graph or remember.
Yes. I think it's. Yes, I think it's so. You have actions to color, and you can color from here, from this step. You can color with another color that costs 1, and with the same color, and that costs 0. But as you can see, to color this is impossible for the graph coloring problem. So you go to a terminal node, and that costs infinity because it is insane to color this. So you have states. These states are partial color graphs, and the node T, the terminal node, where everything is there, and actions to color. We write UK all actions for the state xk, and cost the number of colors used, the cost of paths, and we know this like the function g of xk and uk. Okay, so this is the dynamic programming model. You can see for each state xk, we can define the value function g prime of xk, the minimal cost from xk to t. Finding minimal cost on a dynamic programming model is equivalent to solve a shortest path problem. It means in our case to find g of the singleton one. You can see here the path is the minimal cost from 1 to t. Yes. Bellman's equation says that the value function g in the state xk can be written as this, where uk is a set of all actions for xk, and f of xk uk denotes the next step with this action uk. So if you are in the current state xk, you have many possibilities for each action, and for each action you have a next step. And the Bellman's equation says that if you that the value function here is equal to the minimum of all lower actions, the cost of all lower actions plus the value function of the next step. However, it is difficult to calculate the tree of possibilities for given graph and to find the value function g star. For this, we have applied rollout technique. Rollout technique is a dynamic programming technique. It consists in approximating the value function by a heuristic function h. So it's the same way for reasoning. You are in the current state and you want to minimize by, but for a heuristic. Heuristic, it's very similar to the value function. So it's the same idea, but you change here, not the value function of the next step, and you take the heuristic of the next step. This technique defines a policy to walk through this graph. You are here, for example, next zero, and you calculate here in all next nodes, you calculate the heuristics and you take the minimum of this and you walk in this way. So to stop calculating the heuristic in each step, that can be very, very cost. To stop calculating the heuristic in each step of our dynamic system, we have associated to each state, to each partial colored graph, a lower bound L of the xk. Xk, remember, is a partial colored graph. If the heuristic in xk is equal to the lower bound in xk, it is not necessary to follow with the algorithm, and we can stop it there. And this is the algorithm. And it's the same idea. You go with the heuristics, and when the heuristics is equal to the lower bound in this step, you stop the process and you continue with the heuristic. How we construct the lower bound? We take P, a partial coloring graph of G, and we define a new graph associated with this partial color graph. This graph is called the quotient graph. So it's the graph that identifies the nodes with the same color in the same class and keeps them color nodes with the same structure. Okay. If the chromatic number of GP, which is the minimum number of colors for G starting with P, we have that the chromatic number of this graph starting with P is equal to the chromatic number of this quotient graph. This is the advantage. So taking lower bounds for this quotient graph, it's the same as taking lower bounds for partial colored graphs. So using this, we have created some implementations of this. I want to show you this implementation, the demo. We have constructed first to construct this, we have constructed a random graph generator such that we know exactly its chromatic number for each graph. I will present an example. For example, here we have constructed a graph with 78 vertices with chromatic number 6. And it's important to know accurately the chromatic number to test our algorithm. And for this graph with 78 vertices with chromatic number 6, we have run our algorithm and we have the following results. After 10 steps, we follow with our heuristics, and the heuristics and the lower bound, our algorithm has said that that our number is 8. So we could paint with 8 colors this graph of 78 vertices. It is not the optimal, but it is very close to the optimal. You can check and play with our demo if you want. I can send you the slides and you can click here, and here is our demo. It's a little bit slow in this moment. And in practice, we have used the spectral lower bounds for this graph, this quotient graph, the prime. However, we are working in a future version, and this future version, it will include the roots of unity hypercube heuristics and our other results and your question also. Thank you. Muchas gracias. Thank you.
Questions? Like, you can make one more comment. So there is a notion of there's a notion of a semi-definite extension complexity of a polytope or its slack matrix, and it's kind of related to the things that you were talking about. But essentially, what happens is like this: you have vertices of it, so it will be kind of similar to your set. You have vertices of a polytope, right? And then you have facets, right? So facets are linear functions of the vertices, and you record the values. So you have finitely many functions, and then what you want to show is you want to show that you find the description. You want to show that the facets are non-negative on vertices. And the way that you do it is to write the equation of the facets as sum of squares on the vertices. And now there is a question of what is the smallest subspace from which you can certify the negativity of all the facets, and that actually has a geometric interpretation as like the smallest dimension that you can represent your polytope as a projection of the point PSD matrices. So, but I don't know if people have looked at doing the same certification as multipliers and whether it has any geometric meaning. Of course, people have not looked at any permission things in this context, but even for real things, I think there can be some interesting questions related to kind of choosing the optimal subspace. And it might be.
Yes. Yes, really, I didn't know this approaching, but I will think about this because I didn't know.
Other questions or suggestions?
So maybe I can just make a small comment maybe on this place, but doesn't matter. So are you aware of the approach of doing half color and by using the huge sets?
Sorry, I didn't hear.
So you can also attack the half color in question using the Hilbert huge sets. So a graph is calculable if a certain system has a solution, and supposed to finite. But it's different, it's by checking whether a certain system has a solution or not, and then we want to say that it doesn't have a solution because it's so exceeded a good definition. That's 32 says that one lies the idea.
Okay,
So
okay.
I'm not saying I'm just mentioning this to you, it's because somehow it's kind of using our some express approach, and there is also an approach we are approaches. It's worked by Jesus de Lua and for all sorts of approaches.
Okay. It was it would be amazing if you can send me this because I didn't hear you. I didn't hear about this.
But maybe just
Yes, yes.
Feedback?
Thanks again.
Okay. Okay.
And I'm enjoying the end of the 7. You want to go to the